Hello and welcome to this video on how crystals are made at home, synthetically and naturally. Crystals of all kind are reasonably common. Quartz is used in clocks and more, silicon for microprocessors, diamonds, while being exceptionally rare by comparison, find their way into wedding rings, and rock drill bits. Salt is used for cooking, preserving, and beauty. The availability of different crystals is why they have significantly different value. Where you can buy a diamond for half your value, a mountain of quartz has almost none. This is why the creation of a crystal in a laboratory or factory is so important for industrial applications. It lowers the price of crystals and increases the availability. To get a crystal, you need two things: pressure and heat. When you combine the necessary ingredients in an environment with incredibly high heat and pressure, you get crystals. For diamonds, this is carbon. Each is made by joining the elements that make up the crystal. This in turn forms a lattice. This lattice is ideally only made by involving the molecules that you need for it, but you can get mistakes and inclusions. Mistakes or substitutions are where elements are substituted, and this in turn disrupts the lattice, but it does not break the pattern. Inclusions do not fit into the lattice or make up part of it. This prevents the lattice from being consistent and is why they are not part of the crystal. It is very similar to large carbon deposits in steel, which is made from a combination of carbon and iron. You can do simple experiments to show how crystals are formed, but the same basic principles apply whether it's a home-based experiment or a complete industrial setup that involves many different technical aspects. All of them need your basic material. For example, rubies, which need corundum. They also require the other ingredients which help to give them their color. Things like aluminium oxide, chrome, titanium, vanadium, iron, and others. Emeralds need their own composition. As mentioned with diamonds, they need almost pure carbon. In a ideal situation, all of this is crushed together and melted. This forces all the parts to line up into a nice, neat lattice. The shape is maintained by the long cooling time, which minimizes the chances of the lattice being disrupted by that sudden change in temperature. You can see this to some degree in the simple home demonstration. You may know this from school. You dissolve salt, borax, Epsom salts, or another chemical that will form a crystal into hot water until it is saturated. That is, no more will dissolve in the water. For our example, this is about 3 tablespoons, although that will vary a little bit. You then soak a string in the same solution and let it dry. This will be the initial point where your crystals start to clump and grow from. You now add this string that's going to be the catalyst back into the solution and let it stand for several days. After a few days, you should see the salts being deposited on the string and growing. If you add food dye, you can layer this to create different colors. In this case, it occurs for 2 reasons. The first is simply that as water evaporates out of the open container, it can't hold onto those salts, and so they begin to aggregate. The second is because the solution is saturated, and it begins to cool down. The dissolved salts will fall out of their solution, and so they will become deposited on that string. This is somewhat similar to how crystals in the depths of Earth cool slowly and form a stable solid, by the slow but sure deposition of the necessary material over time. That's why the long cooling period for naturally occurring crystals is so important. In terms of doing this on scale for industry, it has a big flaw. Using the saturated solution approach, it produces very weak and relatively useless crystals. Industrial production of synthetic crystals takes this process and amplifies it several thousand-fold. First is the purity. It uses much more pure mixtures, and it has a more explicit and effective ratio or ingredient mix. This means that you can add extra elements as and where and how you want. These will impart things like strength, durability, and so on. This can be done every time to create a consistent outcome without worrying about exhausting a great mine, different environments, geographies, having to create new infrastructure, and more. Once the needed ingredients are gathered, they are heated to a point at which they melt. This temperature could be as low as 1500 degrees Celsius or as high as 3000 degrees Celsius, that being roughly 2800 to 5500 degrees Fahrenheit. While the ingredients are mixed together and they're compacted, the compacting pressure needs to be incredibly high as well as the heat. The amount of pressure needed is somewhere between 5.2 to 10.4 megapascals. This is somewhere between 0.75 to 1.5 by 10 to the 106th power pounds per square inch. That is an incredibly high pressure. The advantages of this are that you get the same result nearly every time with relatively few imperfections. This consistency and the fact you can do it on a scale means you can then use the same, for example, diamonds for something like drill tips, or you could create reasonably consistent products for uses in watches or other devices like that that need a consistent result. Naturally occurring diamonds, for instance, and other crystals for that matter, often don't have the same consistency, and that's where they differ, other than the fact that they naturally occur from these synthetically created crystals. The value is not so much that they're better, but that they're rarer. In many ways, it's arguable that the consistency of synthetically created crystals is better for many applications because they're easier to work with, you get more usable product, and you don't need to worry about imperfections and flaws. But otherwise, the process is the same sort of system. High heat and high pressure, often much deeper under the Earth's crust. Crystals can be formed from a very simple means to a very complicated industrial process and millennia-long natural mechanisms. It's something you can show for yourself and see for yourself through simple experiments and demonstrations. Thank you for watching this video. If you've found it interesting, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions that you have below.